Hello everyone, my name is Tenindra and I'll be presenting our paper, Hierarchical Graph Traversal for Aggregate K-Nearest Neighbours Search in Road Networks for ICAPS 2020. So our context is in road network graphs. So as input, we're provided a road network graph G equals VE, where V is a set of vertices, which you might consider as road network intersections, and E is a set of edges, which you might consider as the road network segments connecting intersections. Each edge also has a weight, for example, the travel time to traverse the edge. So a closely related problem to the problem we work on in our paper is the K-nearest neighbour query. So in a KNN query, as input, we're provided an object set O, for example, which might be all of the restaurants in a city. We're also provided the location of the agent, Q, for example, a diner. So a KNN query asks the question, what is the nearest object to Q? So if we were to use Euclidean distance as the crow flies, we might consider O2 as the nearest object in our example in the figure. However, if we use network distance, which uses the actual route that we would take through the road network, then O1 is actually closer. So using road network distance is beneficial in that it's more accurate and it's more versatile, as we can use other metrics like travel time. So our problem is actually slightly different. We study the aggregate K-nearest neighbour query. So this is different in that previously we only considered a single agent, whereas in this case, we want to find the nearest object to multiple agents. For example, 3 friends might want to meet at a McDonald's near to them. Which McDonald's out of the 3 in the figure should they meet at? So AkNN query, in addition, takes as input an aggregate function, for example, sum, and it also takes a set of agent locations, Q. So the idea is to aggregate individual distances from each agent to an object and then rank objects by their aggregate score. So in this figure, for object O2, we consider the distance from each agent and we aggregate it using the function. So we're still using network distance for the added benefit of accuracy and versatility. So our example might become the question, which McDonald's minimizes the sum of the travel times over all diners? So the motivation to study this problem is that it's not efficient to compute the distance to every object. The typical solution in problems like these is to heuristically retrieve likely candidates until all results are found. Ideally, meaning we don't retrieve every single object. But we find that for AkNN heuristics, the existing heuristics are either borrowed from the KNN techniques and are not suitable for use in AkNN search, or they're not accurate enough to be used for network distance. So one of these heuristics is the expansion type heuristic. So this has largely been borrowed from KNN search. And the idea is to expand from each query vertex, encountering candidates as we expand. But the best AkNN candidates are probably not likely to be near to any one query vertex. So in our example in this figure, O4 seems like the most likely candidate for the aggregate nearest neighbor. However, it would be encountered last in the expansion heuristic. Another approach is to use a hierarchical search. So for example, let us say we divide space such that we group objects. For example, in this figure, we are using a quadtree and objects are grouped by quadrants. We further divide the space recursively. For example, quadrant 4 is divided into 4 further quadrants that are its children. So the idea is to then search the most promising regions in a top-down recursive manner, and this allows us to pinpoint the best candidates anywhere in space, avoiding the problems of the expansion-based approach, hopefully. So Then it begs the question, how do we decide which regions are promising? Most techniques will use a lower bound score for all objects in a region. So past work has used R-tree as the index for all the objects, and a Euclidean distance lower bound for the minimum bounding rectangle containing all the objects. So this is not particularly accurate for road network distance, as we saw in the previous example earlier in an earlier slide. So what's really needed is a data structure for accurate hierarchical lower bound search in graphs, and we find that no such data structure exists. So one way to improve on the Euclidean heuristic is to use something called landmark lower bounds. So let's say we pre-compute distances from landmark vertices to all other vertices in the graph. Then we can use the triangle inequality to compute a relatively accurate lower bound. But this technique only allows a small number of landmarks. Otherwise, the space cost will really balloon. And it's also not suitable for hierarchical search because these landmarks are not localized. So to address these shortcomings, we propose the compacted object landmark tree, or COLT. So firstly, we partition the graph recursively, resulting in a subgraph tree similar to the one in the figure. Then we choose localized landmarks in every level of the subgraph. Finally, this index structure is compacted based on the object set O to save space. So COLT maintains a number of values in order to make the hierarchical traversal possible. So non-leaf nodes and leaf nodes in the tree structure stores the minimum distance to any object in a subgraph from a landmark, and also the maximum distance. This stored values allows us to compute an accurate lower bound for any tree node. So similar to the previous case, we can do a top-down search starting from the root node for a hierarchical traversal. Once we reach a particular node, we compute a lower bound based on the previous equation for each child node, and then we recursively evaluate the best child, evaluate the child with the best score. So leaf nodes also store an object distance list. And the idea is to find the object in this list with the minimum aggregate lower bound. These object distance lists actually display an interesting property for common aggregate functions in that they preserve convexity. So this means there's a minimum value that we can easily find using a modified binary search. So our experimental setup consists of several data sets. We use the US road network graph with 24 million vertices and 58 million edges. We also obtain real-world POIs from OpenStreetMap for the US in order to use with this graph. So we also compare against two competing methods, IER and NVD. IER is a hierarchical search technique, but using a Euclidean heuristic. NVD is the state-of-the-art expansion heuristic for KNN search. So we find that COLT performs up to an order of magnitude faster than competing techniques. COLT tends to perform better on dense POI sets, and the reason for this is that when POIs are closely packed together, it's difficult to differentiate them. So a better heuristic will perform better. So in the case of sparse POI sets, the less effective heuristics like NVD and IER perform relatively better. But that being said, COLT still outperforms all techniques on all data sets. So we also conducted some sensitivity analysis, and we find that COLT maintains the improvement for varying parameters like the number of routes K and the number of agents, and varying aggregate functions like max and sum. We also find that COLT also performs quite well on heuristic efficiency metrics, not just query time. Our index comes at a lightweight pre-processing cost, and we find that this aligns with our theoretical analysis as well, which we discuss further in the paper. Thank you for your time.